Imagine a predator longer than a city bus, longer than Tyrannosaurus rex, longer than any land-based killing machine that has ever walked this planet. Now imagine that for nearly 100 years, scientists couldn't agree on what it looked like, how it moved, what it ate, or even how it lived. Imagine that the only original fossils were destroyed in a bombing raid during World War II, leaving researchers to rebuild the story of the greatest predator in history from almost nothing. That is the story of Spinosaurus aegyptiacus, and it is one of the strangest, most maddening, most spectacular detective stories in the entire history of paleontology. Most people, when they think of the ultimate predator, think of Tyrannosaurus rex. Hollywood made sure of that. But here is what the science actually says. Spinosaurus was longer. Spinosaurus was heavier by some estimates. Spinosaurus had a skull nearly 2 meters long, lined with conical teeth that could punch through bone like nails through wet paper. And Spinosaurus carried on its back a structure so bizarre, so anatomically extreme, that paleontologists are still arguing about what it even was. A sail? A hump? A display structure? A thermal regulator? The debate has lasted a century, and it has not ended. But the shape of its back is not even the most unsettling thing about this animal. What truly drives scientists to the edge of reason is something far more fundamental. For 100 years, nobody could agree on what kind of animal Spinosaurus actually was. Was it a land predator? Was it semi-aquatic? Did it walk on 2 legs or 4? Did it hunt fish in shallow rivers, or did it pursue and kill massive dinosaurs on dry land? Every time a new fossil surfaced, every time a new study was published, the answer changed, and sometimes it changed completely. There is a reason Spinosaurus has been called the most controversial dinosaur in history. Not the most famous, not the most terrifying, the most controversial. Because every answer it gives us is wrapped inside 3 new questions, and every discovery seems to contradict the one before it. We are going to go through all of it. The original discovery in the scorching Egyptian desert, the catastrophic loss of the fossils, the decades of silence and confusion, the stunning new finds in the Moroccan Sahara that rewrote everything, the studies that tore the scientific community apart, and the questions that remain completely unresolved even today, right now, as you are watching this. Because here is the truth about Spinosaurus. We have been studying this animal since 1912. That is over 100 years of research, debate, excavation, and analysis. And in many ways, we still do not know what we are looking at. That is not a failure of science. That is science at its most honest, its most dramatic, and its most alive. So let us go back to the beginning, to a desert that barely exists anymore as it once was, to a German aristocrat with a shovel, a theory, and no idea that what he was about to pull out of the rock would haunt paleontology for the next century. Let us go to Egypt. 1910. The Bahariya Oasis sits in the western desert of Egypt, roughly 350 kilometers southwest of Cairo. Today, it is a quiet depression in the sand, dotted with palm trees and small villages. But in 1910, it was one of the most remote and brutal field locations a paleontologist could choose. Temperatures regularly exceeded 50 degrees Celsius. Water was scarce. The nearest railway was a day's journey away. And yet a German nobleman named Richard Markgraf was out there, crawling through the sandstone formations on his hands and knees, looking for bones. Markgraf was not a trained scientist. He was a fossil hunter, a collector, a man with an extraordinary instinct for finding things that had no business being found. He worked for Ernst Stromer von Reichenbach, a Bavarian paleontologist based in Munich who had become obsessed with the idea that North Africa was hiding an entirely unknown chapter of dinosaur history. Stromer had read the geology. He had studied the rock formations. He believed the Bahariya beds dated to the Cretaceous period, roughly 95 to 100 million years ago, and he believed they were hiding something extraordinary. He was right. He had no idea how right he was. Markgraf began sending bones back to Munich. First, the remains of a massive sauropod, then a strange crocodile-like creature, then another predator, and another. The Bahariya Formation was not hiding one unknown species. It was hiding an entire lost ecosystem, a world that had never been documented, a predator community so dense and so violent that modern paleontologists still struggle to explain how it functioned. But in 1912, Markgraf found something that stopped everything else. It was a partial skeleton embedded in the sandstone. Vertebrae, ribs, partial limb bones, and rising from the back of the creature, neural spines of absolutely absurd proportions. Some of these spines, projecting upward from the vertebrae, were nearly 2 meters tall. Not the whole animal, not the skull, not the limbs, just the spines on its back, and they were taller than a grown man. Markgraf carefully documented the site, excavated what he could, and shipped the material to Munich. Ernst Stromer received the fossils, laid them out in his laboratory, and began to piece together what kind of animal he was dealing with. The skull material was fragmentary but revealing. The teeth were long, conical, and slightly curved, not the blade-like serrated teeth of a typical large theropod. They looked almost like the teeth of a large crocodile. The jaw was long and narrow, more like a gharial than like the deep, powerful jaws of a tyrannosaur. The neck vertebrae suggested a long, flexible neck. And those spines, those impossible, towering spines. Stromer published his formal description in 1915, in the middle of the First World War. He named it Spinosaurus aegyptiacus, spine lizard of Egypt. He classified it as a large theropod dinosaur, placed it in its own family, and noted that the neural spines were unlike anything previously recorded in any dinosaur. He suggested they supported a sail of skin similar in concept to the sail of Dimetrodon, the Permian reptile that had lived nearly 300 million years earlier. And then the world moved on. There was a war to survive, and Spinosaurus, for the moment, was filed away. For 2 decades, very little happened. Stromer continued his work. He described several other extraordinary predators from Bahariya, including Carcharodontosaurus, a massive theropod with blade-like teeth that may have rivaled Spinosaurus in size. He built a picture of a lost Cretaceous world, a coastal floodplain crisscrossed with rivers bordered by a shallow sea teeming with enormous creatures that science had never imagined. But the Spinosaurus material, fragmentary as it was, remained puzzling. There was not enough of it to reconstruct the animal with any confidence. How long was it really? How heavy? How did it move? What did it actually eat? Without a complete skeleton, without a full skull, without limb bones that told a clear story, Stromer could only gesture at the outline of a giant and admit that the details were missing. He stored the fossils in the Bavarian State Collection of Paleontology in Munich, where they sat through the 1920s and the 1930s. And then came 1944. April 24, 1944. The Royal Air Force conducted a bombing raid on Munich. The museum took a direct hit. The building that housed the Bavarian State Collection was destroyed. Ernst Stromer's Spinosaurus was gone. every original bone, every vertebra, every neural spine. Every fragmentary piece of skull that had survived the journey from the Egyptian desert to a laboratory in Bavaria, burned and buried under rubble. Stromer had actually written to museum officials before the raid, pleading with them to move the collections to safety. He had seen what was coming. He understood the danger. His requests were denied. He outlived the destruction of his life's work by only 4 years, dying in 1952. His son had already been killed on the Eastern Front. His Spinosaurus was ash and dust. What remained of the most mysterious predator in history was nothing but Stromer's original published illustrations, his technical drawings, his written descriptions, and a handful of photographs of fossils that no longer existed. For the next 50 years, paleontologists trying to understand Spinosaurus were essentially working from a ghost. They had the outline, they had the measurements Stromer had recorded, they had the drawings, but the physical evidence, the irreplaceable three-dimensional reality of the bones themselves, was gone forever. Think about what that means for a scientist. You cannot re-examine the material. You cannot run new analyses. You cannot apply modern imaging technology. You cannot catch errors or reinterpret details in light of new discoveries. You are locked permanently into the quality of a description written during the First World War by a scientist working with the tools and the theoretical frameworks of 1915. Spinosaurus became something rare in paleontology, a dinosaur that was simultaneously famous, frequently discussed, and almost completely unknown. And into that vacuum of knowledge, something predictable happened. People started guessing. Scientists started extrapolating. Artists started imagining. And for decades, the reconstructions of Spinosaurus were built not on hard evidence, but on inference, comparison, and the particular assumptions of whoever was doing the reconstructing at any given time. Some scientists estimated it at around 12 to 14 meters long. Others pushed it to 17 or 18. Some depicted it as a slightly unusual large theropod, basically a T-Rex with a decorative sail on its back. Others suggested something more exotic, something that didn't fit neatly into any existing category. The sail itself was a constant source of argument. Was it a thermoregulatory structure used to absorb heat in the morning and radiate it in the afternoon? Was it a display feature used to attract mates or intimidate rivals? Was it a fat storage hump, like the hump of a camel, used to sustain the animal through lean seasons? Every few years, a new paper would argue for one interpretation or another, and none of them could be definitively tested because the original fossils were gone. Then, in the 1990s, something changed. New expeditions began working in North Africa. New fossils started surfacing, and slowly, agonizingly, piece by piece, the ghost began to take on flesh. But what the new bones revealed was not what anyone expected, and it would trigger a scientific controversy that is still burning today. The Kemkem beds of southeastern Morocco are not a comfortable place to work. The region sits on the edge of the Sahara, where temperatures in summer push past 50 degrees Celsius, and the wind carries fine sand that gets into everything. The rock is hard, the terrain is broken and irregular, and the fossils, when you find them, are often fragmentary, scattered, and mixed together in ways that make identification a genuine challenge. Local fossil hunters had been working the area for decades, pulling out teeth and bones and selling them through informal markets that stretched across North Africa and into Europe. For a long time, professional paleontologists largely overlooked the Kemkem. The fossils coming out of it were intriguing but difficult to contextualize. There was no systematic excavation. There was no stratigraphic control. Bones were being found but not recorded properly, which meant their scientific value was limited. That began to change in the 1990s and accelerated dramatically in the 2000s. And it was through this region, through the chaotic, sun-baked, commercially exploited fossil beds of Morocco, that Spinosaurus began its slow and startling return. The first significant development came not from a dramatic single discovery, but from a gradual accumulation of material. Teeth, mostly. Long, conical, unserrated teeth that matched the profile of Stromer's original description. Vertebrae with unusually tall neural spines. Skull fragments. These pieces were surfacing from the Kim, from rock dated to roughly 95 to 100 million years ago, the same age as the Bahariya Formation in Egypt. The same animal. A different country. A continent that looked nothing like it does today. In the Cretaceous period, the Sahara did not exist. The region that is now North Africa was a vast coastal floodplain, cut through by enormous river systems draining into the Tethys Sea to the north. The climate was hot and humid. Dense vegetation grew along the riverbanks. The rivers themselves were enormous, wide and shallow in places, deep and powerful in others, teeming with fish of extraordinary size. Onchopristis, a sawfish with a rostrum lined with barbed teeth, reached lengths of up to 8 meters. Giant coelacanths cruised the deeper channels. Enormous lungfish buried themselves in the mud during dry seasons. It was a world built around water. And Spinosaurus, it was becoming clearer, was built for water in ways that no large theropod had ever been before. But it was one man more than anyone else who forced this realization into the scientific mainstream, and his path to Spinosaurus was as unlikely and dramatic as the animal itself. Nizar Ibrahim was born in Germany to a German mother and a Moroccan father. He grew up with a fascination for paleontology and eventually found himself doing fieldwork in the Kim region, working through the informal fossil markets and the local networks of collectors that had been feeding museums and universities with North African material for decades. He was looking for Spinosaurid material specifically, trying to piece together a better picture of this infuriating, elusive animal. In 2008, a local fossil hunter approached Ibrahim with a cardboard box. Inside were bones. A partial skeleton, the man explained, found somewhere in the Kim. He could not give a precise location. The bones had been excavated informally, and the site had not been documented. But the material was extraordinary. A partial skull, vertebrae, limb bones, and, crucially, something that would become the center of an enormous scientific argument. The bones of the hind limbs, which were dramatically, almost shockingly, shorter than any comparable large theropod. Ibrahim recognized the significance immediately. But without knowing exactly where the fossils had come from, without being able to relocate the site, the material could only tell part of the story. He needed the context. He needed the rock. He needed to go back. What followed was a search that Ibrahim himself has described as bordering on the impossible. The Kim is vast. The collector who had brought him the box had no GPS coordinates, no clear description of the site, only vague memories of a journey across featureless desert. Ibrahim spent years trying to track down the location, working through intermediaries, following fragments of information that led nowhere. Then, years later, by a coincidence that sounds invented but is documented, Ibrahim recognized the fossil hunter in a cafe in a Moroccan town. The man agreed to take him back to the site, and the team relocated the excavation. What they found confirmed everything the initial material had suggested and added new details that made the picture even stranger. Ibrahim brought the fossils to the Natural History Museum in Milan and to a team that included Paul Sereno of the University of Chicago, one of the most prominent dinosaur hunters in the world. Together, they built a reconstruction of Spinosaurus that drew on the new Moroccan material, on Stromer's original descriptions, and on comparisons with other spinosaurids that had been discovered in the intervening decades in places like England, Brazil, and Niger. The reconstruction they published in 2014 in the journal Science was unlike anything the paleontological community had seen before. The Spinosaurus of Ibrahim and Sereno's 2014 paper was not the upright two-legged theropod that had dominated reconstructions for a century. It was something far stranger, far more extreme. The hind limbs were short and dense, with bones that showed unusually high density, a feature associated in modern animals with semi-aquatic lifestyles. The feet were broad and flat. The nostrils were positioned high on the skull, far back from the tip of the snout, similar to the position of nostrils in crocodilians that need to breathe while mostly submerged. The neural spines were not a thin sail, but potentially a taller, thicker structure, more like a hump than a fin. And in their functional reconstruction, the team proposed something that sent shockwaves through the paleontological community. Spinosaurus, they argued, was not primarily a land animal. It was a river monster. Not just a dinosaur that waded into rivers to catch fish, the way a grizzly bear wades into a salmon stream. Not just an opportunist that occasionally got its feet wet, but a genuine semi-aquatic predator, spending the majority of its life in or near the water, moving through river systems, hunting beneath the surface, physically adapted to an aquatic lifestyle in ways that no other large dinosaur had been. The short, dense hind limbs were consistent with a paddling motion rather than terrestrial locomotion. The high nostril position allowed surface breathing. The long, narrow skull with its conical teeth was ideally shaped for catching slippery fish underwater. The overall proportions of the body were low-slung and horizontally oriented, not the upright posture of a typical large theropod, but the flattened, elongated profile of an animal that moved through water. Ibrahim's team went further. They proposed that Spinosaurus moved on all four limbs on land, quadrupedally, like a crocodile, rather than bipedally like Tyrannosaurus or Allosaurus. The forelimbs were long and robust. The center of mass was positioned far forward, making upright two-legged locomotion unstable and inefficient. The headline that emerged from the 2014 paper was stark and dramatic. Spinosaurus was the first dinosaur known to science that had adapted to an aquatic lifestyle. The largest predatory dinosaur ever discovered was not a land hunter. It was a river predator, a fish-eating giant that ruled the waterways of Cretaceous North Africa the way no creature before or since had ruled them. The reaction from the scientific community was immediate, divided, and extremely loud. Some paleontologists embraced the reconstruction enthusiastically. The evidence for semi-aquatic adaptations seemed compelling. The bone density data was real. The nostril position was real. The proportions of the limbs were real. And the ecology of the Kim environment, that vast river system teeming with enormous fish, provided a plausible and even elegant context for an animal shaped the way Spinosaurus appeared to be shaped. Others pushed back hard. The criticism came from multiple directions. Some questioned whether the skeleton used in the reconstruction truly represented a single individual, or whether bones from different animals had been accidentally combined. The informal excavation of the Moroccan material without proper stratigraphic documentation was a genuine scientific weakness. How could anyone be certain that the short hind limb bones came from the same animal as the tall-spined vertebrae and the elongated skull? Others questioned the quadrupedal locomotion hypothesis directly. Donald Henderson of the Royal Tyrrell Museum in Alberta published a study using computer modeling that suggested Spinosaurus would have been an extremely poor swimmer, too top-heavy, too unstable, more likely to roll over than to propel itself effectively through water. His models indicated that the animal would float awkwardly and struggle to maintain directional control in a current. Paul Barrett of the Natural History Museum in London was among those who expressed skepticism about the overall reconstruction, noting that the evidence for obligate aquatic lifestyle was suggestive but not conclusive, and that alternative interpretations of the anatomical features were possible. The argument was not just scientific. It was, in a quieter way, also professional. The 2014 paper had been published with enormous fanfare, accompanied by a National Geographic documentary, a museum exhibition, and widespread media coverage. The reconstruction had reached millions of people before the scientific community had finished evaluating it. That kind of public impact raises the stakes of being wrong in ways that a technical paper quietly published in a specialist journal simply does not. Nizar Ibrahim defended the reconstruction vigorously. The bone density data was solid, the nostril placement was solid, and the overall pattern of features taken together pointed consistently towards semi-aquatic adaptation. The argument continued. And then, in 2019, it got dramatically more complicated. In 2019, a team of researchers led by Nizar Ibrahim published a new paper in the journal Nature. The subject was a structure that sounds almost mundane compared to the dramatic controversies that had surrounded Spinosaurus for decades. It was a tail. Specifically, it was a series of tail vertebrae recovered from the Kimkim beds of Morocco, vertebrae that had been sitting in the collections of the Natural History Museum in Milan, waiting for someone to understand what they were looking at. When the team analyzed these vertebrae carefully, what they found stopped the argument in its tracks. Not because it ended the debate, but because it fundamentally changed the terms of it. The tail vertebrae of Spinosaurus were unlike anything previously recorded in a theropod dinosaur. The neural spines projecting upward from each vertebrae were extraordinarily tall and blade-like. Not the short triangular projections seen in most dinosaurs, not even the moderately elongated spines of some other large theropods. These were long, flat, and flexible in a way that immediately suggested something to anyone who had spent time studying modern aquatic animals. They looked like the vertebrae of an eel, or a crocodile, or a newt. They looked like the vertebrae of an animal whose tail was designed not to balance a body moving on land, but to propel a body moving through water. The team built a physical model of the tail and tested it in water. The results were striking. The tall-spined tail of Spinosaurus generated thrust in water with an efficiency that was dramatically higher than the tails of other dinosaurs tested under the same conditions. It moved through water the way a paddle moves through water, pushing against the resistance of the fluid, generating forward propulsion. According to the biomechanical analysis published alongside the paper, the tail of Spinosaurus was approximately 8 times more effective at generating aquatic thrust than the tail of a typical terrestrial theropod like a young crocodile used as a comparative model. 8 times. That is not a marginal difference. That is not a slight advantage. That is the difference between an animal that occasionally splashes around in shallow water and an animal that is genuinely, powerfully built to swim. The 2019 paper landed like a depth charge in the ongoing debate about Spinosaurus. For those who had been skeptical of the 2014 reconstruction, this was new and harder to dismiss evidence. You could argue about bone density, you could argue about nostril placement, you could argue about whether the skeleton was a composite of different individuals. But a tail shaped like a paddle, with biomechanical data showing it could generate real aquatic thrust, was a different kind of argument entirely. Donald Henderson, who had published the swimming model suggesting Spinosaurus would be unstable in water, responded that the new tail data was significant, but that questions about overall aquatic locomotion remained. A powerful tail does not automatically make an animal an efficient swimmer if the rest of its body is poorly suited to the task. The debate, he maintained, was not over, but the tail vertebrae shifted the balance of probability in a way that was difficult to ignore. Even scientists who had been cautious about the 2014 reconstruction acknowledged that the tail evidence was genuinely compelling, and it opened a new line of questioning that is, in some ways, even more interesting than the original controversy. If Spinosaurus had a tail adapted for swimming, what exactly was it doing in the water? The obvious answer, the answer that had dominated the Spinosaurid discussion for years, was fish. The Chem-Chem environment was packed with them. Onchopristis alone, that enormous sawfish, represented an almost absurd abundance of large prey. The conical, unserrated teeth of Spinosaurus were perfectly suited to gripping slippery fish rather than cutting through the flesh and bone of large terrestrial prey. The long, narrow skull, sometimes compared to the skull of a gharial, was mechanically optimized for fast lateral sweeps through water to catch fish, not for the powerful crushing bite of an animal that needed to subdue large, struggling prey on land. The isotopic evidence supported this. A study published in 2010 examining the oxygen isotope ratios preserved in Spinosaurus tooth enamel found values that were consistent with a semi-aquatic lifestyle. The ratio of oxygen isotopes in an animal's teeth reflects the water it drinks and the environment it inhabits. Semi-aquatic animals like crocodiles and hippos show different isotopic signatures from fully terrestrial animals. The Spinosaurus teeth fell consistently in the semi-aquatic range, closer to crocodilians than to large terrestrial theropods. So the fish-eating hypothesis had multiple lines of support. Tooth morphology, skull shape, isotopic chemistry, nostril position, and now, a tail built like a paddle. But here is where the story gets genuinely complicated. Because the evidence for fish eating, as strong as it is, sits alongside evidence that Spinosaurus was also doing something else. Something that does not fit neatly with the image of a gentle river giant scooping up fish in its long jaws. On the teeth and bones of Spinosaurus, researchers have found something unexpected. Bite marks and wear patterns that are not consistent with a diet of fish alone. Scratch marks on bones of large dinosaurs from the same formation that match the tooth dimensions of Spinosaurus. And one finding in particular that has never been satisfactorily explained away. In the stomach region of at least one Spinosaurid specimen, researchers found the bones of a young sauropod dinosaur. Not fish bones, not the remains of a sawfish or a lungfish or any aquatic creature. The bones of a large terrestrial herbivore, a dinosaur that had no business being at the bottom of a river. Now, this evidence comes not from Spinosaurus aegyptiacus itself, but from a closely related Spinosaurid, Baryonyx walkeri, found in England. Baryonyx is a smaller, better understood relative of Spinosaurus, and its stomach contents, documented since its discovery in 1983, show both fish remains and the bones of a young iguanodon, an animal that lived on land. Does Baryonyx's diet tell us anything about Spinosaurus? Possibly. Spinosaurids as a group may have been more ecologically flexible than the pure fish-eating narrative suggests. They may have been opportunists, taking fish as their primary prey, but not passing up the opportunity to ambush terrestrial prey near the water's edge, the way a modern Nile crocodile will eat fish for months and then drag a wildebeest underwater without hesitation. But this creates a tension at the heart of the Spinosaurus story that has not been resolved. If Spinosaurus was truly semi-aquatic, spending most of its life in the water, then how did it hunt large terrestrial dinosaurs? And if it was flexible enough to take large land prey, does that change our understanding of how it moved on land? Can an animal with short, dense hind limbs and a low center of mass really pursue a large dinosaur across dry ground? Some researchers have suggested that the ambush model is the answer. Spinosaurus, they argue, did not chase prey on land. It waited at the water's edge, like a crocodile, and seized animals that came to drink. A creature that spends most of its time in the water does not need to be a fast, agile runner. It needs to be fast enough for long enough to close the gap between the water and an animal standing at the bank. Others are not convinced. The biomechanical analysis of Spinosaurus locomotion on land suggests it would have been genuinely awkward moving quickly in a fully bipedal posture. If it walked on all fours, as Ibrahim's 2014 paper proposed, it may have been even slower and less maneuverable. Ambush predation requires a burst of speed over a short distance. Whether Spinosaurus could generate that burst in the right direction at the right moment is something the bones alone cannot tell us with certainty. And then there is the question that looms over the entire discussion, like one of those 2-meter neural spines. If Spinosaurus was so well adapted to water, if its tail was a paddle and its limbs were dense and its nostrils were high and its teeth were conical and its whole body was oriented toward an aquatic lifestyle, then why was it so enormous? Semi-aquatic predators in the modern world do not grow to 17 or 18 meters. Crocodiles are large, certainly, but the biggest living crocodilians reach around 6 or 7 meters. The largest semi-aquatic mammals, the hippos, are enormous by terrestrial standards, but nowhere near the scale of Spinosaurus. The biggest purely aquatic predators, the sperm whales and the orcas, live in the ocean, where buoyancy solves the problem of supporting massive body weight. A 17-meter animal wading in a river system is carrying its full weight against gravity every time it moves onto land or into shallow water. That is an enormous energetic cost. Why did Spinosaurus grow so large if its lifestyle was semi-aquatic rather than fully oceanic? One possibility is that size itself was the advantage. In a river system full of enormous fish and competing predators, being the largest animal in the water meant having access to the largest prey and the ability to drive competitors away. The Chimchem environment was not a peaceful place. Carcharodontosaurus, one of the largest terrestrial predators ever discovered, was living in the same region at roughly the same time. So was a massive crocodile-like archosaur called Sarcosuchus, which reached lengths of up to 9 or 10 meters. So were other large predators. The competition for food was extreme by any measure. In that context, being enormous was not a luxury. It was survival. But it still does not fully answer the question. And the question of why Spinosaurus grew to the size it did and how it sustained a body of that size in a river ecosystem rather than an open ocean remains one of the genuinely open problems in Spinosaurid biology. The tail paper of 2019 pushed the scientific consensus further toward accepting a genuinely semi-aquatic Spinosaurus than it had ever been before. But it did not close the debate. It redirected it. Instead of arguing about whether Spinosaurus was aquatic, researchers began arguing about how aquatic it was and what exactly that meant for how it behaved, how it fed, and how it survived. And just as that new phase of the argument was gaining momentum, the excavations in Morocco produced something new. Something that did not simplify the picture at all. Something that suggested Spinosaurus might have been even stranger than anyone had yet imagined. There is a principle in ecology that most biologists treat as close to a law. It is called the competitive exclusion principle, and it states that two species competing for exactly the same resources in exactly the same space cannot coexist indefinitely. One will outcompete the other. One will be driven to extinction, or pushed into a different niche, or forced to adapt until it is no longer truly competing with the original rival. The natural world, the principle insists, does not tolerate redundancy at the top of the food chain. The Kem-Kem ecosystem of Cretaceous North Africa violated this principle so aggressively that when paleontologists first began to understand the full picture, some of them refused to believe it. Because Spinosaurus was not the only giant predator in the Kem-Kem. It was not even the only giant predator of its approximate size. The formation that produced the bones of Spinosaurus also produced the bones of Carcharodontosaurus saharicus, a massive terrestrial theropod with blade-like serrated teeth, a deep, powerful skull, and a body length estimated at up to 13 or 14 meters. Carcharodontosaurus was not a fish-eater. It was a pursuit predator, built for hunting large terrestrial dinosaurs, with the teeth and jaw mechanics to cut through flesh and crush bone on land. And that was not all. The same beds produced Deltadromeus agilis, a large, lightly built theropod whose long, slender limbs suggest it was fast, possibly a pursuit predator operating at a different scale from the giants. They produced the remains of enormous sauropods, potential prey animals of staggering size. They produced multiple species of large fish, giant crocodilians including Sarcosuchus imperator, enormous turtles, and pterosaurs with wingspans that reached beyond 6 meters. When Paul Sereno and his colleagues began systematically analyzing the Kem-Kem predator community in the 2000s, they described it as the most predator-dense ecosystem yet discovered in the fossil record. The ratio of large predatory animals to large herbivorous animals in the Kem-Kem appeared to be dramatically higher than in any comparable Cretaceous environment. In places like the Hell Creek Formation of North America, which produced Tyrannosaurus rex, the ratio of apex predators to large herbivores follows a pattern broadly consistent with modern ecosystems. The Kem-Kem did not. A study published by Sereno and his colleagues calculated that the Kem-Kem had something like 3 times as many large predators relative to available prey as would be expected from ecological modeling based on modern ecosystems. 3 times. That is not a rounding error. That is a fundamentally different kind of ecological structure. How was this possible? How did an ecosystem support multiple giant predators simultaneously without collapsing under the weight of predation pressure? The answer, researchers proposed, lay in the extraordinary productivity of the river system itself. The Cretaceous waterways of North Africa were not like modern African rivers. They were vastly larger, vastly more productive, and they were teeming with prey of a scale that has no modern equivalent. Onchopristis, that enormous sawfish, was essentially an 8-meter-long package of protein available to any predator large enough to subdue it. The giant coelacanths and lungfish added to an almost absurd abundance of aquatic food resources, and the sauropods and other large herbivores that lived along the riverbanks represented an enormous terrestrial food source on top of the aquatic one. The key, the researchers argued, was ecological partitioning. The different predators were not actually competing for the same resources in the same space. Spinosaurus was taking fish and aquatic prey from the rivers. Carcharodontosaurus was hunting large dinosaurs on the floodplains. Deltadromeus was taking smaller, faster prey that neither giant could efficiently catch. The ecosystem was not violating the competitive exclusion principle. It was demonstrating it in action, with each predator occupying a sufficiently distinct niche that direct competition was minimized. This is an elegant hypothesis. It makes intuitive sense, and it is supported at least partially by the anatomical differences between the predators. Spinosaurus and Carcharodontosaurus had fundamentally different feeding apparatus. Their teeth were different, their skulls were different, their likely hunting strategies were different enough that imagining them as direct competitors for identical prey is genuinely difficult. But the hypothesis has a problem. Several problems, actually. The first is that ecological partitioning in modern ecosystems, even in the richest and most productive environments on Earth, does not typically produce the predator density that the Kim appears to show. The Serengeti, the most productive large mammal ecosystem currently known, has lions, leopards, cheetahs, hyenas, wild dogs, and multiple other predators. But it also has enormous herds of wildebeest, zebra, and gazelle that number in the millions. The ratio of predators to prey is maintained within boundaries that prevent the prey populations from being consumed faster than they can reproduce. The Kim would have needed prey populations of staggering size to sustain its predator community. And while the rivers were clearly enormously productive, the terrestrial prey community, as best as we can reconstruct it from the fossil record, was not dominated by vast herds of fast-reproducing, medium-sized herbivores. It was dominated by sauropods, enormous but slow-reproducing animals that do not replenish their numbers quickly. The second problem is taphonomic. Taphonomy is the study of how organisms become fossils, and it is full of biases that can distort our picture of ancient ecosystems. Large predators with dense bones preserve better than small, fragile-boned herbivores. Riverside environments, like the Kim floodplains, tend to concentrate the bones of animals that died near water, which may mean that aquatic and semi-aquatic predators are overrepresented relative to terrestrial herbivores that lived and died further from the river. The apparent dominance of predators in the Kim may be partly a reflection of preservation bias rather than true ecological structure. Nizar Ibrahim and his collaborators have pushed back against the taphonomic explanation, arguing that even accounting for preservation bias, the density of large predators in the Kim is genuinely anomalous. But the debate continues. And then there is a third problem, one that sits specifically at the intersection of the Kim ecology discussion and the Spinosaurus biology discussion, a problem that has not been satisfactorily addressed by either side. If Spinosaurus was truly semi-aquatic, spending most of its life in the water, then it was essentially occupying the same ecological space as Sarcosuchus. Sarcosuchus imperator, the enormous crocodile-like archosaur, was itself a giant aquatic or semi-aquatic predator with a long skull and conical teeth, extremely well suited to catching large fish and aquatic prey in the same river system. Sarcosuchus reached lengths of 9 or 10 meters and weights estimated at around 8 tons. It was not as large as Spinosaurus, but it was enormous by any standard. Two giant, semi-aquatic, fish-eating predators in the same river system at the same time. How did the competitive exclusion principle tolerate that? One possibility is that they were partitioned by size. Sarcosuchus may have taken prey too small for Spinosaurus to bother with, while Spinosaurus targeted the largest fish and occasionally large terrestrial prey at the water's edge. Size-based niche partitioning is well documented in modern crocodilian communities, where different species of crocodile coexist in the same river by targeting prey of different sizes. Another possibility is that they were partitioned by behavior or microhabitat. Perhaps Sarcosuchus was more strictly aquatic, remaining in deeper channels, while Spinosaurus used shallower, more marginal aquatic habitats. Perhaps they avoided each other through territorial behavior that we have no direct fossil evidence of. Or perhaps they competed directly, and the fossil record is showing us a snapshot of a genuinely unstable ecological moment, a community that was in the process of sorting itself out, that would not have remained in its current configuration for long on geological timescales. We do not know. And the honest answer is that with the fossil evidence currently available, we probably cannot know with certainty. What we can say is that the Kim-Kim ecosystem was unlike anything that exists on Earth today. It was a world of giants stacked on giants, predators of extraordinary size competing and coexisting in ways that challenge our understanding of how ecosystems function. And at the center of it, in the rivers and along the banks, was Spinosaurus, the largest predatory dinosaur that ever lived, doing something that no large dinosaur had done before or since. But understanding what Spinosaurus was doing in that ecosystem requires understanding the animal itself at a level of detail that the fossil record has only recently begun to provide. And some of the most important new details have come not from new bones, but from new technology applied to old questions. In 2020, a study published in the journal eLife used a technique called computational fluid dynamics to model how Spinosaurus actually moved in water. This is the same kind of modeling used by aerospace engineers to analyze airflow over wing surfaces, applied instead to water flow around a moving dinosaur. The results suggested that the paddle-like tail of Spinosaurus, combined with its overall body shape, would have produced efficient undulatory swimming locomotion, the side-to-side motion used by fish and crocodilians, rather than the up and down motion used by whales and dolphins. The model suggested Spinosaurus swam more like a large fish or a crocodile than like any mammal. Its tail moved laterally, sweeping through the water in broad strokes, generating thrust with each stroke. The body flexed along its length. The short hind limbs contributed minimally to propulsion, consistent with their interpretation as limbs primarily used for stability in water or slow movement on land, rather than powerful terrestrial locomotion. This was important not just as a description of movement, but as an ecological statement. Undulatory swimmers in the crocodilian mode are most effective in slower-moving water, in rivers and floodplains, rather than fast-flowing mountain streams or open ocean. They are ambush predators, rather than pursuit predators, using patience and sudden acceleration over short distances, rather than sustained high-speed chasing. They are generalists in terms of prey type, taking whatever is available and accessible, from large fish to terrestrial animals at the water's edge. In other words, the computational fluid dynamics model painted a picture of Spinosaurus that was entirely consistent with a crocodilian ecological role, scaled up to a size that dwarfs any crocodilian that has ever existed. A crocodile the size of a city bus, with the neural spines of something from a nightmare, living in rivers teeming with fish the size of cars, alongside terrestrial predators that would have been considered apex hunters in any other ecosystem on Earth.
It is a picture that is simultaneously more coherent and more extraordinary than anything that was imagined when Ernst Stromer first laid out those impossible bones in his Munich laboratory in 1915. But coherent does not mean complete, and there are aspects of Spinosaurus biology that the bones, the isotopes, the computer models, and the ecosystem reconstructions have still not explained. The most obvious one has been there since the very beginning. The sail, or the hump, or whatever it actually was. After 100 years, we still do not fully understand why Spinosaurus carried one of the most extreme anatomical structures in the entire history of vertebrate life on its back. And the answer, when we examine the evidence carefully, is stranger than most people realize. Let us start with the basic anatomy, because the basic anatomy is already extraordinary. The neural spines of Spinosaurus, the bony projections rising vertically from the vertebrae of its back, were not uniform along its length. They varied dramatically depending on their position. The spines over the hips and mid-back were the tallest, reaching heights that, in the largest individuals, approached or possibly exceeded 1.5 to 2 meters above the vertebra itself. That means the highest point of the structure on Spinosaurus's back was somewhere between 2.5 and 3 meters above the ground, assuming an animal of typical reconstructed proportions. Higher than any door you have ever walked through. Higher than most trucks. The spines were laterally compressed, meaning they were flattened from side to side rather than round in cross-section. They were blade-like, and they tapered toward their tips. In some specimens, the tips appear to have been slightly expanded or rounded, suggesting the presence of cartilage or some other soft tissue at the apex. Now here is the question that has generated more papers, more arguments, and more diagrams than almost any other single feature of any dinosaur in history. What was covering those spines? If the spines supported a thin sail of skin, like the sail of Dimetrodon or the modern basilisk lizard, then the structure was essentially a large, flat surface of skin stretched over a bony framework, well supplied with blood vessels, able to absorb or radiate heat efficiently, highly visible to other animals, and structurally fragile relative to its surface area. If the spines were embedded in a thick mass of fat and connective tissue, like the hump of a bison or a camel, then the structure was a bulky, three-dimensional mass rising from the back, good for energy storage, less useful for thermal regulation, less visually dramatic from a distance, but more robust and physically substantial. If the spines supported something in between, a moderately thickened skin structure with both display and physiological functions, then the answer is more nuanced and harder to test. And if, as a small number of researchers have proposed, the spines were covered in muscle rather than fat or thin skin, then the structure was something else entirely. A muscular ridge that changed the animal's movement mechanics and center of mass in ways we have not fully modeled. Each of these possibilities has been seriously argued in the scientific literature. Each has evidence in its favor, and none of them has been definitively proven or ruled out, because soft tissue does not fossilize under normal conditions. The bones are all we have, and bones alone cannot tell you what was on top of them. The thermoregulation hypothesis was the first and in many ways the most intuitive. It was proposed by Stromer himself, drawing on the analogy with Dimetrodon. The logic runs as follows. A large, flat surface covered in skin and richly supplied with blood vessels can function as a biological radiator. In the morning, when the animal is cold, it orients the sail toward the sun, absorbing heat rapidly and warming the blood flowing through the surface. In the heat of the day, it orients away from the direct sun, allowing convective cooling as blood circulates through the surface and releases heat to the air. This is a plausible mechanism. It works in principle, and it would have been genuinely useful for a large animal living in the hot, humid environment of Cretaceous North Africa, where managing body temperature could have been a significant physiological challenge. But the thermoregulation hypothesis has several problems that have become more apparent as our understanding of Spinosaur physiology has developed. First, the mathematics of heat exchange do not strongly support a thermoregulatory function for a structure of this shape and size. A thin sail is reasonably effective at absorbing heat. It is much less effective at radiating heat because the same large surface area that absorbs radiant energy from the sun
also absorbs radiant energy from the warm environment surrounding the animal. In a hot tropical environment, a sail would tend to make the animal hotter, not cooler, for most of the day. Modern analyses of the thermal properties of sail structures suggest they are more effective in cooler, more variable climates than in the consistently hot tropics. Second, if thermal regulation was the primary function, you would expect to see similar structures in other large dinosaurs living in similar climates. The Chem-Chem ecosystem was full of large animals facing the same thermal challenges that Spinosaurus faced. Carcharodontosaurus did not have a sail. The sauropods did not have sails. The crocodilians did not have sails. If a sail was such a useful thermoregulatory adaptation in this environment, why did only Spinosaurus develop one? Third, and perhaps most significantly, the semi-aquatic lifestyle hypothesis that has dominated the recent literature actually undermines the thermoregulation argument. An animal that spends much of its time in water does not need to thermoregulate through a sail. Water is an enormously effective thermal buffer. An animal immersed in a river is constantly exchanging heat with the surrounding water, which moderates its body temperature far more effectively than any sail could. If Spinosaurus was truly semi-aquatic, a thermoregulatory sail on its back becomes not just unnecessary, but actively counterproductive, creating drag in the water and providing no meaningful benefit for an animal that was thermally buffered by its aquatic lifestyle. The display hypothesis has gained ground as the thermoregulation argument has weakened. Under this model, the neural spines and whatever soft tissue covered them formed a visual signal, a structure whose primary function was communication with other members of the same species. Display structures are extraordinarily common in the animal kingdom. Peacock tails, elk antlers, the crests of cassowaries, the dewlaps of iguanas, the color patches of mandrills. Animals invest enormous resources in structures whose sole measurable function is to be seen. Display structures typically serve two related purposes. They communicate dominance or fighting ability to rival males, reducing the cost of actual physical combat by allowing animals to assess each other visually. And they signal genetic quality to potential mates, allowing females to choose partners based on visible evidence of health and development. Under the display hypothesis, the neural spines of Spinosaurus were the dinosaurian equivalent of antlers. Large, elaborate, energetically costly to grow and maintain, and honest signals of the animal's quality as a competitor and a mate. An individual Spinosaurus with taller, more symmetrical neural spines was advertising its genetic health. An individual with damaged or asymmetrical spines was advertising weakness. This hypothesis is difficult to test directly, but it has indirect support from several directions. Spinosaurids as a group show variation in the height and shape of their neural spines that is consistent with individual variation in a display structure. Studies of other dinosaur crests and structures, notably the crests of hadrosaurs, which were once thought to be thermoregulatory but are now understood primarily as acoustic and visual display structures, have shown that elaborate anatomical features in dinosaurs were frequently driven by social signaling rather than physiological necessity. And there is a broader argument from biomechanics. A structure 2 meters tall on the back of an animal that is trying to move efficiently through water is a significant hydrodynamic liability. It creates drag. It destabilizes the animal in current. It costs energy every time the animal swims. If the structure served a critical physiological function like thermoregulation, that cost might be worth paying. If it served only a display function, the same cost calculation applies. Animals routinely carry enormous physiological burdens for the sake of display. The peacock's tail reduces its ability to escape predators by a measurable amount. Evolution maintains it anyway because the mating advantage outweighs the survival cost. The hump hypothesis, which gained particular prominence following a paper published by a team including Paul Sereno and several biomechanics specialists, argues that the neural spines were embedded in a thick mass of adipose tissue, fat, forming a hump rather than a sail.
The analogy most frequently cited is the bison, or the American buffalo, which has enormously elongated neural spines over its shoulders that are embedded in a massive muscular and fatty hump rather than supporting a thin skin sail. The evidence cited for the hump interpretation includes the cross-sectional shape of the spines themselves. In animals with true sails, the neural spines tend to be extremely thin and laterally compressed throughout their length, maximizing surface area while minimizing mass. The neural spines of Spinosaurus, while laterally compressed, are not as thin relative to their height as would be expected in a pure sail structure. Some researchers have argued this is more consistent with spines that were surrounded by substantial soft tissue, which would have provided mechanical support and distributed the stresses of the structure more evenly. A fat hump would also have made ecological sense for an animal living in the unpredictable boom and bust cycles of a seasonal river system. During times of plenty, when the rivers were full of fish and prey was abundant, the animal could build up fat reserves in the hump. During lean seasons, when prey was scarce and the rivers ran low, those reserves could be metabolized to sustain the animal through periods of nutritional stress. But the hump hypothesis has its own problems. A large, fat-filled hump on the back of a semi-aquatic animal would have been buoyant, which would have complicated diving and deep-water movement, and the cross-sectional analysis of the spines, while suggestive, is not conclusive. The same spine morphology could be consistent with a moderately thickened skin sail rather than a true hump. A study published in 2020 by a team from the University of Portsmouth, led by David Martill, took a different approach to the question.
Rather than analyzing the spines themselves, Martill's team looked at the spacing between the spines and the way they were articulated with each other. Their analysis suggested that the spines were closely spaced and interlocked in a way that was inconsistent with a freestanding sail flapping in the wind. A true sail, they argued, requires the spines to be somewhat independent of each other, able to flex relative to each other as the skin between them moves. The Spinosaurus spines, in their analysis, appeared too rigidly connected for that. Their conclusion was that the structure was more likely a stiff, solid dorsal crest than a flexible sail, probably covered in thick skin with relatively little capacity for movement or flexibility. Not quite a hump in the bison sense, but not a thin, flexible sail either. Something in between, a rigid dorsal ridge, possibly brightly colored or patterned, primarily serving a display function. This is, it must be said, still a hypothesis. The paper generated responses from researchers who interpreted the articular surfaces of the spines differently, arguing that the articulation was consistent with a degree of flexibility that would allow a functional sail. The debate did not end with the Portsmouth paper. It merely added a new voice to an argument that has been running for over a century. And this is perhaps the most honest thing that can be said about the structure on Spinosaurus's back after 100 years of study. We know what the bones look like. We know how tall they were. We know their cross-sectional shape. We have measured the spacing between them and analyzed their articular surfaces. We have run thermal models and biomechanical models and compared them to every relevant living analog we can find. And we still do not know what was covering them. We do not know if Spinosaurus looked like a creature with a dramatic, towering sail that cut through the air above the river surface as it waded through the shallow.
We do not know if it looked like a massive humped giant, its back rising in a smooth curve of fat and skin. We do not know what color it was, whether the structure was used for display, thermal regulation, energy storage,
or some combination of all three. What we know is that whatever was on its back, it was extraordinary. It was the most extreme dorsal structure in the history of large terrestrial vertebrates. No dinosaur before or since developed anything comparable in scale and elaboration. And the animal that carried it was already, even without the spines, one of the most anatomically unusual creatures that has ever lived. But if the structure on its back is a mystery, it is at least a mystery with clear physical boundaries. We can measure the bones. We can constrain the possibilities. There is another mystery surrounding Spinosaurus that is not so easily constrained. A mystery that goes to the heart of how we understand growth, development, and the life history of this animal. A mystery that only became apparent when researchers started looking not at individual specimens, but at the whole population of Spinosaurus material and asking a question that seems almost too basic to have been overlooked. How old were the animals we have found? And what happened to the young ones? There is a technique in paleontology called osteohistology. It is, in its simplest description, the study of bone tissue under a microscope. When you cut a thin section through a dinosaur bone and examine it under magnification, you see something that looks remarkably like the rings of a tree. Layers of bone tissue deposited year by year as the animal grew, each layer slightly different in density and structure from the ones around it. By counting these lines of arrested growth, as paleontologists call them, you can determine with reasonable confidence how old an individual animal was when it died.
Osteohistology has transformed our understanding of dinosaur growth and life history over the past 3 decades. It has shown us that some dinosaurs grew with extraordinary speed, reaching adult size in a fraction of the time it takes a comparably sized modern reptile to mature. It has shown us that others grew more slowly, following trajectories more similar to large modern crocodilians. It has revealed differences between species, between sexes within species, and between individuals within populations that no other technique could detect. When researchers applied osteohistology to the available Spinosaurus material, the results raised a question that nobody had fully anticipated. The specimens we have from the Kim and from comparable North African formations are, by the evidence of their bone tissue, not fully mature animals. The neural spines, the limb bones, the vertebrae, the skull material that forms the basis of our reconstruction of Spinosaurus, all of it comes from individuals that were still growing when they died. They were large, enormously large, but they were juveniles or subadults in biological terms, animals that had not yet reached their maximum potential size. Think about what that means. The animal we have been reconstructing, the 17-meter river giant, the creature whose proportions have driven 100 years of scientific argument, may not represent a fully grown Spinosaurus. It may represent an adolescent, a large adolescent certainly, but an animal that, had it survived to full maturity, might have been significantly larger. How much larger is genuinely unknown. Growth curves in large dinosaurs are difficult to extrapolate because the relationship between juvenile and adult dimensions is not linear and varies enormously between species. But some estimates, based on comparisons with other large theropods and on the degree of skeletal immaturity visible in the available material, have suggested that a fully mature Spinosaurus could have reached length approaching 20 meters or possibly beyond. 20 meters. That is longer than the largest confirmed specimen of any other predatory dinosaur. It would make Spinosaurus not just the largest predatory dinosaur we know of, but potentially the largest predatory animal that has ever lived on land, by a significant margin. These estimates are speculative.
They are not based on direct measurement of a fully mature skeleton because no fully mature Spinosaurus skeleton has been found. They are extrapolations, and extrapolations carry uncertainty. But the fact that our best known specimens appear to be subadults is not speculative. That is what the bone tissue shows. And it immediately raises a second question, one that is in some ways even more puzzling than the first. Where are the young ones? In most dinosaur-bearing formations, the fossil record, imperfect as it is, preserves animals across a range of sizes and ages. In the Hell Creek Formation, you find juvenile Tyrannosaurus rex alongside subadults and fully mature giants. In the Morrison Formation, you find juvenile sauropods alongside the enormous adults. Size distributions in well-sampled dinosaur populations follow roughly the pattern you would expect from a real biological population, with more young animals than old ones, and a gradual progression of sizes from hatchling to adult. The Spinosaurus record does not look like that. Small Spinosaurus specimens, juvenile animals in the early stages of growth, are extraordinarily rare, almost absent. When researchers have surveyed the Kim material systematically, looking for small spinosaurid bones that would represent hatchlings or juveniles in the first few years of life, they find almost nothing. The record jumps from occasional fragmentary material suggesting very small individuals to the large subadult specimens that form the core of our knowledge of the animal, with almost nothing in between. This is deeply strange. Baby Spinosaurus had to exist. The animal reproduced, as all dinosaurs did, by laying eggs. Hatchlings emerged from those eggs. Those hatchlings grew through a series of juvenile stages before reaching the subadult and adult sizes represented in the fossil record. The biology is not in question, but the fossil record of those early life stages is essentially blank. Why? Several explanations have been proposed, and none of them is entirely satisfying. The most straightforward is taphonomic bias. Small, lightly built juvenile bones are far less likely to preserve and be found than the large, dense bones of older individuals. A hatchling Spinosaurus would have had bones barely larger than those of a modern chicken, thin-walled, fragile, easily destroyed by weathering, transport, and scavenging. Even in a rich fossil formation, small juvenile bones are consistently underrepresented relative to large adult bones. This is a universal feature of the dinosaur fossil record, and it applies to Spinosaurus as it applies to every other species. But the degree of underrepresentation in the Spinosaurus record seems anomalous even by the standards of the general taphonomic bias. Researchers who have worked extensively in the Kim note that juvenile material of other large predators, while rare, does exist. Small teeth of Carcharodontosaurus have been found. Small crocodilian bones appear throughout the formation. The virtual absence of small Spinosaurus material is more extreme than the general pattern of juvenile underrepresentation would predict. A second possibility is microhabitat separation. If juvenile Spinosaurus lived in different environments from adults, their remains might be concentrated in areas that have not been well sampled or that preserve fossils less effectively. Many modern crocodilians show strong ontogenetic habitat shifts, with juveniles living in shallow, marginal aquatic habitats like reed beds and swamps, while adults occupy the main river channels and open water. If juvenile Spinosaurus used habitats that were geographically or ecologically separated from the floodplain environment that produced the adult material, their bones would simply not appear in the same fossil beds. This is a plausible hypothesis, and it fits with what we know about semi-aquatic animals more broadly. But it is, at present, an untested inference. We have no direct evidence of what habitat juvenile Spinosaurus used. We only know that, wherever they lived, their bones are not turning up where we are looking. A third possibility is more uncomfortable. It is possible that the virtual absence of small Spinosaurus juveniles in the fossil record reflects something real about the biology of the animal, something about how it reproduced, how it raised its young, or how the young survived that we do not yet understand. Perhaps juvenile Spinosaurus were not present in the main river environment at all during their early years. Perhaps they were born in environments far from the main river systems and only moved into the river habitat as they approached subadult size. Perhaps the mortality pattern of young Spinosaurus was so extreme that the window during which small individuals existed was very short, and the probability of fossilization correspondingly low. None of these possibilities can be confirmed or ruled out with the current evidence. But the question of the missing young connects to a broader question about Spinosaurus life history that has only recently begun to receive serious attention.
How fast did Spinosaurus grow? And how long did it live?
For most large theropod dinosaurs, the growth rate question has been addressed through osteohistology combined with body mass estimates at different life stages. Tyrannosaurus rex, for example, is now known to have had a rapid growth phase during its teenage years, adding hundreds of kilograms per year during peak growth before slowing dramatically as it approached adult size. The growth strategy of large dinosaurs in general appears to have been broadly similar to that of modern birds rather than modern reptiles, with rapid growth to adult size followed by a long adult plateau rather than the slow, indefinite growth seen in crocodilians and other large reptiles. The Spinosaurus osteohistological data is frustratingly limited because of the small number of specimens that have been properly sampled. What data exists suggests a growth pattern broadly consistent with other large theropods, with relatively rapid juvenile growth and a peak growth phase in the subadult period. But without material spanning the full growth range from hatchling to fully mature adult, the growth curve cannot be accurately reconstructed. What the osteohistological data does suggest, with more confidence, is something about the specimens themselves. The large subadult individuals from the Kim appear to have been in their peak growth phase when they died, animals in the most energetically demanding period of their lives, consuming food at the highest rate they would ever require, growing rapidly, and not yet reproductively mature. Reproductively immature. That is another detail that complicates the picture. If the best known Spinosaurus specimens were not yet sexually mature, then the reconstruction we have is not of an animal in its prime reproductive years. It is of an animal that was still in the process of becoming what it would ultimately be.
The behaviors associated with reproduction, including whatever role the dorsal structure played in display and mate attraction, the territorial behavior of fully mature adults, the social dynamics of a population of giant semi-aquatic predators, all of this is invisible to us because we have not found the animals at the stage of life when those behaviors would have been most pronounced. It is as if everything we knew about lions came from studying adolescent males before they had grown their manes. We would have the basic anatomy, we would have a general sense of the animal's size and proportions, but we would be missing the most visually dramatic features of the adult, and we would have no direct evidence of the social and reproductive behavior that drives the most important aspects of the animal's life history. The parallel is not exact, but the principle holds. The Spinosaurus we know is an incomplete picture not just because the fossil record is fragmentary, but because the fragments we have come disproportionately from a specific and unrepresentative phase of the animal's life. And then, in 2022, a discovery was made in the Kim that added a new dimension to the question of Spinosaurus life history. Not a new skeleton, not a new skull, something much smaller, and in its own way, much more significant. Footprints.
a series of trackways preserved in the Kim Formation, analyzed by a team including Nizar Ibrahim and several ichnologists, specialists in fossil footprints and traces, revealed something that no amount of skeletal analysis could have shown directly. The trackways showed an animal moving in shallow water. The prints were deep at the toe tips and shallow at the heel, exactly the pattern you would expect from an animal that was wading, pushing off against a substrate while partially buoyed by water. The stride pattern was consistent with slow, deliberate movement rather than the rapid locomotion of a pursuit predator.
And the trackway showed a left-right alternation of footprints that suggested, with reasonable confidence, quadrupedal or at least partially quadrupedal locomotion in the water. The size of the prints was consistent with a large Spinosaurus individual, and their location, preserved in what the geological analysis identified as a shallow, slow-moving riverine environment, placed the animal exactly where the semi-aquatic hypothesis had predicted it would be found. Footprints are not perfect evidence. A single trackway cannot tell you everything about an animal's behavior, but they provide something that bones cannot. They show the animal alive, moving, interacting with its environment at a specific moment in time. They collapse the distance between us and a creature that lived 95 million years ago and allow us to see, for just a moment, not a reconstruction or a hypothesis or a computer model, but the actual act of a living animal moving through its world. 95 million years ago, something enormous waded through a shallow river in what is now Morocco. Its feet pressed into the soft sediment. Its weight shifted from one side to the other as it moved. The water rose around its legs and perhaps its belly, and somewhere above the surface, rising from its back, was that extraordinary structure, sail or hump or crest, catching the light of a Cretaceous sun. It left its footprints in the mud, and the mud turned to stone. And 95 million years later, we found them. That is what paleontology is, not just bones and measurements and isotope ratios and computer models. It is the recovery, one fragment at a time, of moments that should have been lost forever. But even with footprints, even with all the new evidence of the past decade, there are aspects of Spinosaurus that remain genuinely, profoundly unresolved. And one of them strikes at the most fundamental question you can ask about any animal. What was it, truly, in the hierarchy of its world? Was it the apex? Was it challenged? Was it, despite its enormous size and extraordinary adaptations, vulnerable in ways that its skeleton does not reveal? The answer requires us to look at what else was living alongside it. And what was living alongside Spinosaurus was, by any reasonable standard, terrifying. There is a thought experiment that paleontologists occasionally use to illustrate the strangeness of the Kim ecosystem. Take the largest predator in any modern terrestrial environment, the Siberian tiger, the polar bear, the Nile crocodile, the saltwater crocodile. Now imagine placing 2 or 3 animals of comparable or greater size in the same environment, competing for the same space, the same water, the same prey. Now make all of them significantly larger than anything alive today. Now remove every ecological safety valve that modern ecosystems use to prevent total collapse. That is approximately what the Kim looked like 95 million years ago. We have already discussed Carcharodontosaurus saharicus and Sarcosuchus imperator at some length. But to truly understand the world that Spinosaurus inhabited, those 2 animals are only the beginning. The full roster of large predators in the Kim Formation reads like something assembled by a committee specifically tasked with imagining the most extreme ecosystem possible. Deltadromeus agilis
was not as large as Spinosaurus or Carcharodontosaurus, but what it lacked in mass, it may have compensated for in speed. Its limbs were extraordinarily long and slender relative to its body, more similar in proportion to an ostrich or an emu than to the robust, heavily built limbs of most large theropods. Estimates of its body length range from around 8 to 9 meters, with a body mass considerably lower than its length might suggest.
The combination of long limbs and relatively light build has led some researchers to propose that Deltadromeus was among the fastest large predators of the Cretaceous, a pursuit hunter capable of sustained high-speed locomotion in ways that Spinosaurus and Carcharodontosaurus were not. However, it must be noted that Deltadromeus is itself a controversial animal. Its classification has shifted multiple times since its description by Paul Sereno and colleagues in 1996. Some researchers have questioned whether it belongs among the theropods at all, and its ecological role in the Chimchim community remains debated. What is clear is that it was large, it was built for speed, and it was present. Then there were the pterosaurs. The flying reptiles of the Chimchim were not the small insect-catching creatures of popular imagination. Anhanguera and related pterosaurs with wingspans reaching 5 or 6 meters soared above the river system, diving for fish in the way that modern gannets and pelicans dive, but at a scale that modern birds cannot approach. Whether these animals interacted directly with Spinosaurus in any meaningful ecological sense is unclear. They were almost certainly not competing for the same prey in the same way, but they were part of a community of large fish-eating animals that suggests the rivers of the Chimchim were extraordinarily productive, rich enough to sustain multiple large predators of completely different body plans simultaneously. And below the surface of those rivers, the competition was, if anything, even more extreme. Onchopristis numitis, the giant sawfish, was itself a predator of considerable capability. Its rostrum, that elongated, tooth-lined extension of the snout, was not merely a passive filter or a defensive weapon. Studies of modern sawfish behavior show that the rostrum is used actively to slash through schools of fish, stunning or injuring multiple prey items in a single lateral sweep, then collecting the stunned fish from the water around it. An 8-meter Onchopristis performing this behavior in a shallow river was a genuinely dangerous animal, capable of inflicting serious wounds on any predator attempting to seize it without care. The interaction between Spinosaurus and Onchopristis has been a subject of considerable speculation. The conical teeth of Spinosaurus, its long, narrow jaws, its wading locomotion in shallow water, all of these features are consistent with a predator that targeted Onchopristis specifically, approaching from above in shallow water where the sawfish's size and the awkward length of its rostrum would have been disadvantages rather than advantages. Several researchers have suggested that Onchopristis was essentially the primary prey of Spinosaurus, the animal around which the whole extraordinary morphology of the giant Spinosaurid was built. The evidence most frequently cited for this specific predator-prey relationship is a remarkable find from the original Stromer material, documented in his 1915 paper and confirmed by later analysis. Among the Spinosaurus material, Stromer noted the presence of Onchopristis rostral denticles, the barbed teeth that line the sawfish's rostrum, in association with the dinosaur bones. Whether these denticles were stomach contents, suggesting Spinosaurus had eaten Onchopristis, or whether they were simply associated by depositional coincidence, has been debated. But the proximity of the two animals in the fossil record, combined with the anatomical case for Spinosaurus as an Onchopristis specialist, has made the relationship between these two giants one of the more compelling ecological stories in Cretaceous paleontology. But ecological stories in the Chimchim do not stay simple for long.
Because Sarcosuchus imperator was also present, and Sarcosuchus was also large enough to take Onchopristis, and Sarcosuchus had a skull that, in its overall proportions and tooth morphology, was remarkably similar to that of Spinosaurus. Two enormous, long-snouted, conical-toothed, semi-aquatic predators occupying the same rivers, targeting, at least potentially, the same prey. How did they coexist? The size difference provides a partial answer. At around 9 or 10 meters and 8 tons, Sarcosuchus was formidable but significantly smaller than a fully grown Spinosaurus. In a direct competition for the same prey item, Spinosaurus would have won simply through size and displacement. A Sarcosuchus in possession of a large Onchopristis could not have defended its catch against a Spinosaurus that wanted it. The competitive hierarchy, at least for the largest prey items, would have been clear. But Sarcosuchus was not limited to the main river channels. Modern crocodilians are remarkably versatile in their use of aquatic habitats, accessing small channels, seasonal pools, and marginal wetlands that larger animals cannot easily reach. A 9-meter Sarcosuchus could have exploited microhabitats that a 17-meter Spinosaurus could not enter, giving it access to prey resources that were effectively protected from competition by simple geometry. And this brings us to a question that has been raised seriously in the literature but never fully resolved. Did Spinosaurus and Sarcosuchus interact directly? Did they compete, fight, avoid each other? Were there territorial boundaries between them, maintained through display, vocalization, or outright aggression? We have no direct fossil evidence of interaction between these two animals. No bones showing the bite marks of the other. No trackways showing pursuit or confrontation.
The fossil record of behavior is always fragmentary, and the specific evidence for direct Spinosaurus-Sarcosuchus interaction does not currently exist. But the indirect evidence of their coexistence raises the possibility of interactions that would have been extraordinary by any standard. A confrontation between a 17-meter Spinosaurus and a 9-meter Sarcosuchus over possession of a large carcass or a stretch of productive river would have been among the most dramatic predator interactions in the history of life on Earth. Neither animal was a pushover. Sarcosuchus had the dermal armor of a crocodilian, bony scutes covering its back and flanks that would have been highly resistant to the conical, gripping teeth of Spinosaurus, and a bite from a Sarcosuchus jaw, closing with the force that a skull of that size and musculature could generate, would have been capable of severing limbs or crushing bone. The outcome of such an interaction would have depended on context. In deep water, where Sarcosuchus could deploy the death roll and the underwater suffocation techniques used by modern crocodilians, a large Sarcosuchus might have been genuinely dangerous even to a much larger Spinosaurus. On land, or in very shallow water, where Spinosaurus could use its full body weight and reach, the size advantage would likely have been decisive. These are speculations, informed speculations, grounded in what we know about the biomechanics of both animals and the behavior of their modern relatives, but speculations nonetheless. What is not speculation is the broader ecological picture. The Chem-Chem was a place where being large was not enough to guarantee safety. It was a place where multiple giant predators competed for shared resources in an environment that was, by geological standards, temporary and unstable. River systems change. Floodplains shift. Prey populations fluctuate with seasonal cycles and longer-term climatic changes.
An ecosystem as predator-dense as the Chem-Chem was inherently sensitive to any disruption of the prey base. And roughly 94 million years ago, the Chem-Chem ecosystem did collapse. The precise cause is not fully understood. A combination of factors appears to have been involved, including significant sea level changes, shifts in the drainage patterns of the river systems,
and possibly climatic changes that reduced the productivity of the floodplain environment. The formation that produced such an extraordinary diversity of giant predators essentially stops producing them above a certain geological horizon. The Kim giants, Spinosaurus, Carcharodontosaurus, Sarcosuchus, Deltadromeus, all of them disappear from the record at roughly the same time. This was not the end of Spinosaurids as a group. Spinosaurid dinosaurs persisted in various parts of the world for millions of years after the Kim community collapsed. But Spinosaurus aegyptiacus, the specific animal at the heart of our story, the largest predatory dinosaur known to science, appears to have been a product of a very specific set of ecological conditions that existed for a geologically brief window of time and then ended. The world that made Spinosaurus possible was itself extraordinary, and like all extraordinary things in the fossil record, it was temporary. But before we follow Spinosaurus to its end, there is one more chapter of its scientific story that demands attention. Because the debates about its anatomy, its ecology, and its behavior did not end with the 2014 reconstruction or the 2019 tail paper. In the years that followed, a new generation of researchers took aim at some of the most fundamental claims made about this animal, and the resulting controversy became one of the most publicly visible scientific arguments in the history of vertebrate paleontology. The question they asked was blunt, and the answer, depending on who you ask, is still not settled. Could Spinosaurus actually swim? In 2021, a paper appeared in the journal eLife that did something unusual in academic paleontology. It did not just propose a new interpretation of Spinosaurus, it directly and systematically challenged the most prominent reconstruction of the animal that had been published in the previous decade, named the researchers responsible for that reconstruction, and argued that the evidence for semi-aquatic locomotion in Spinosaurus was significantly weaker than had been claimed. The paper was authored by a team led by Paul Barrett of the Natural History Museum in London and included several other prominent researchers in dinosaur locomotion and functional morphology. Its title was precise and its argument was structured, and it landed in the paleontological community like a stone thrown into still water, sending ripples outward that are still moving today. The core argument of the Barrett team was not that Spinosaurus was definitely not aquatic. It was more nuanced and in some ways more damaging than a simple denial. Their argument was that the evidence presented in the 2014 and 2019 papers, while genuinely interesting, did not meet the standard of proof required to support the strong claims that had been made about Spinosaurus as an obligate semi-aquatic predator that spent the majority of its life in the water. Let us go through their specific criticisms, because they are detailed and they are serious. The first concerned bone density. The 2014 Ibrahim paper had cited the unusually high bone density of Spinosaurus limb bones as evidence of semi-aquatic adaptation, noting that high bone density, technically called pachyostosis, is commonly associated with semi-aquatic and aquatic animals because dense bones reduce buoyancy and help the animal maintain depth in water. The analogy cited was with modern manatees, penguins, and other animals that use dense bones as ballast. Barrett's team acknowledged that Spinosaurus bones were dense, but they challenged the interpretation of that density as specifically semi-aquatic. Dense bones, they pointed out, are not exclusively found in aquatic animals. They appear in some large terrestrial animals as a consequence of simple scaling. Larger animals tend to have proportionally denser bones than smaller animals purely as a mechanical response to the stresses of supporting greater body weight. They also appear in animals living in specific environments where particular locomotor demands favor denser skeletal elements. The presence of dense bones in Spinosaurus, they argued, could be explained by its large size and its locomotor mechanics without invoking semi-aquatic lifestyle at all. This is a legitimate point. The problem is that it cuts both ways. Dense bones in Spinosaurus are consistent with semi-aquatic adaptation. They are also consistent with other explanations. Consistency is not proof, and the 2014 paper, Barrett's team argued, had sometimes written as though consistency with semi-aquatic adaptation was equivalent to evidence for it. These are not the same thing. The second criticism concerned the nostril position. The high placement of the nostrils on the Spinosaurus skull, far back from the tip of the snout, had been cited as evidence of semi-aquatic adaptation, analogous to the retracted nostrils of crocodilians that allow breathing while mostly submerged. Barrett's team pointed out that the nostril position in Spinosaurus was not actually as far back as in obligate aquatic or semi-aquatic animals. It was further back than in most terrestrial theropods, certainly, but it had not reached the position seen in highly aquatic animals like crocodilians, where the nostrils are placed almost at the level of the eyes. The Spinosaurus nostril position, they argued, was intermediate, consistent with an animal that spent some time near water, but not necessarily with one that spent the majority of its life submerged. Again, a legitimate point. Intermediate anatomy can mean many things. It can mean an animal in transition between two ecological modes. It can mean an animal that uses multiple environments without being fully specialized for either. It can mean a lineage where the adaptation is present, but not yet fully developed. None of these interpretations requires the conclusion that Spinosaurus was spending most of its time underwater. The third, and in some ways most technically complex criticism, concerned the quadrupedal locomotion hypothesis. The 2014 paper had proposed that Spinosaurus moved on all four limbs on land, based on the short hind limbs and the forward-positioned center of mass. Barrett's team ran their own biomechanical analysis and reached a different conclusion. Their modeling suggested that while the center of mass of Spinosaurus was positioned further forward than in most bipedal theropods, it was not so far forward as to make bipedal locomotion impossible or even particularly inefficient. Large theropods in general have a more forward center of mass than smaller ones, as a simple consequence of their size and proportions. Spinosaurus was extreme, but not uniquely so, and their analysis suggested it was probably a biped on land, like other large theropods, rather than a quadruped. If Spinosaurus was bipedal on land, several of the inferences built on the quadrupedal model begin to weaken. A bipedal Spinosaurus could move more efficiently on dry ground than a quadrupedal one. It could potentially pursue terrestrial prey. It was a more capable land animal than the 2014 reconstruction had implied. The fourth criticism was the one that struck most directly at the foundation of the semi-aquatic hypothesis. Barrett's team revisited the question of whether the Moroccan skeleton used in the 2014 reconstruction actually represented a single individual. This had been a concern since the paper was first published. The informal excavation of the material, without proper stratigraphic documentation, meant that there was no guarantee that the bones came from the same animal. The short hind limbs that had been central to the semi-aquatic argument were particularly concerning in this regard. If those limb bones came from a different, possibly smaller individual than the tall-spined vertebrae and the elongated skull, then the reconstruction was a composite, and the proportions that drove the aquatic hypothesis might be artifacts of combining material from different animals. Barrett's team could not prove that the skeleton was a composite. Nobody could, without being able to re-examine the original site with full stratigraphic control, which was no longer possible. but they argued that the uncertainty was real, significant, and had not been adequately acknowledged in the original publication. Nizar Ibrahim responded to the Barrett paper with force and with detail. On the bone density question, he and his colleagues pointed to additional analyses that had been published since 2014, strengthening the case for pachyostosis as a semi-aquatic adaptation specifically rather than a general size-related phenomenon. On the nostril position, they maintained that even an intermediate position was more consistent with semi-aquatic than fully terrestrial lifestyle. On the locomotion question, they pointed to the 2019 tail paper as independent evidence of aquatic adaptation that did not depend on the limb proportions or the center of mass calculations that Barrett's team had challenged. And on the composite skeleton question, Ibrahim's team published additional material that they argued supported the integrity of the original reconstruction. New preparation of the existing fossils, new analysis of the bone surfaces, and new comparative material from the chem that showed consistent anatomical patterns across multiple Spinosaurid specimens all contributed to a case that the short hind limbs and the tall spines belonged together, to the same animal, or at minimum, to the same species, with consistent proportions across individuals. The argument did not resolve. It intensified. Other researchers weighed in. Some supported Barrett's skepticism. Others sided with Ibrahim's reconstruction. Several published analyses that tried to stake out intermediate positions, accepting some aspects of the semi-aquatic hypothesis while questioning others. A study by Matteo Fabbri and colleagues, published in 2022 in the journal Nature, took yet another approach. Rather than arguing about the specific anatomy of Spinosaurus in isolation, Fabbri's team assembled a large dataset of bone density measurements from hundreds of living and extinct animals across a huge range of body sizes, ecological types, and taxonomic groups. They used this dataset to build a statistical model that predicted aquatic lifestyle from bone density alone, calibrated against animals of known ecology. When they applied this model to the Spinosaurus material, the result was unambiguous. The bone density of Spinosaurus fell squarely in the range of semi-aquatic and aquatic animals, well outside the range of fully terrestrial animals of comparable size. Their model predicted semi-aquatic lifestyle for Spinosaurus with high statistical confidence. More intriguingly, the same analysis produced results for other Spinosaurids that had not been central to the aquatic debate. Baryonyx, the English relative of Spinosaurus, also showed bone density consistent with semi-aquatic lifestyle. So did Suchosaurus, another Spinosaurid known from fragmentary material. The pattern appeared to be a consistent feature of the Spinosaurid lineage as a whole, not an idiosyncratic feature of one unusually large species. This was significant. If Spinosaurids as a group showed bone density consistent with semi-aquatic lifestyle, then the aquatic adaptation was not a unique and improbable extreme reached only by Spinosaurus aegyptiacus. It was a lineage-wide characteristic, a pattern that had been established early in Spinosaurid evolution and maintained across the group. That made evolutionary sense. It meant that the extraordinary aquatic adaptations of Spinosaurus were not a sudden departure from the typical theropod body plan, but the culmination of a long evolutionary trajectory that had been moving in the same direction for millions of years. Barrett's team acknowledged the Fabbri 2022 study as a significant contribution, but maintained that bone density alone, even with a large comparative dataset, could not resolve all the questions about Spinosaurus locomotion and ecology. The argument continued on multiple fronts simultaneously. And then there was the question that both sides of the argument had been dancing around without quite addressing directly. If Spinosaurus was semi-aquatic, what does that actually mean in terms of how it spent its daily life? How much time in the water?
How much on land? Was it like a modern hippopotamus, spending most of the day submerged and emerging to feed at night? Was it like a modern saltwater crocodile, equally capable in both environments and moving between them fluidly depending on opportunity? Was it like a modern gharial, so highly specialized for aquatic life that terrestrial locomotion was genuinely difficult and rare? These are not abstract questions. The answer changes almost everything about how we visualize the animal. A hippo-mode Spinosaurus would have spent most of its visible hours as a bulk of spine and back rising above a river surface, largely invisible and inert from a distance. A crocodile-mode Spinosaurus would have been seen regularly on riverbanks and mudflats, moving between water and land with fluid ease. A gharial-mode Spinosaurus would have been almost never seen on dry ground, a river creature so completely that its terrestrial existence was marginal. No study has definitively answered this question. The bone density, the tail morphology, the nostril position, the isotopic data, all of these lines of evidence are consistent with a range of aquatic intensities from moderately semi-aquatic to highly aquatic. They do not pinpoint a specific point on that spectrum. What they do, taken together, is make one conclusion increasingly difficult to avoid. Spinosaurus was not a typical large theropod that occasionally waded into rivers to catch fish. Whatever the precise degree of its aquatic adaptation, its body was shaped by millions of years of evolutionary pressure toward an aquatic lifestyle in ways that no other large dinosaur shows. It was genuinely, fundamentally different from Tyrannosaurus and Allosaurus and Carcharodontosaurus in a way that goes beyond the shape of its back or the length of its snout. It was something new, something that the theropod lineage had never produced before and never produced again. A giant predatory dinosaur that had, over evolutionary time, begun the journey back toward the water that the earliest vertebrates had made in the opposite direction hundreds of millions of years earlier. The swimming debate has not ended. It will probably not end until a complete, fully mature, undisputedly single individual Spinosaurus skeleton is found with clear provenance and full stratigraphic documentation. That skeleton may exist somewhere in the Kim beds, buried under meters of sandstone, waiting for an excavation that has not yet happened, or it may never be found. The fossil record does not owe us completeness. It gives us what it gives us, and we build the best picture we can from what survives. And what survives is enough to say this: the scientific argument about Spinosaurus is not a sign that paleontology is failing. It is a sign that paleontology is working exactly as it should. Evidence accumulates. Hypotheses are tested. Claims are challenged. Models are revised. The picture improves, slowly and painfully, and sometimes dramatically. But it improves. 100 years after Ernst Stromer first laid out those impossible bones in his Munich laboratory, we understand Spinosaurus far better than he did, and we are more confused about it than ever. Both of those things are true simultaneously, and both of them are signs of a science that is alive. But there is one final chapter of the Spinosaurus story that we have not yet told. One that is not about anatomy or ecology or swimming biomechanics. One that is about time itself. About what happened to Spinosaurus at the end. About how the reign of the largest predatory dinosaur that ever lived came to its close. And about what, if anything, remains of it today. 93 million years ago, something began to change in the world that Spinosaurus had ruled. It did not happen overnight. It did not happen in a single catastrophic moment, the way the asteroid impact 66 million years ago
would later end the age of non-avian dinosaurs entirely. It happened slowly, in the way that geological and climatic changes always happen, across timescales so vast that no individual animal, no individual generation, no individual population could have perceived the shift.
But the shift was real, and it was irreversible, and it was fatal to the ecosystem that had produced the most extraordinary predator in the history of life on land. The Cretaceous was a period of dramatic and continuous geological change. The continents were moving. Sea levels were fluctuating on scales of tens of meters over millions of years. Ocean circulation patterns were shifting as the geometry of the ocean basins changed. And in North Africa, the vast river system that had fed the Kimkim ecosystem, the waterways that had sustained Spinosaurus and Carcharodontosaurus and Sarcosuchus and all the other giants of that extraordinary world, was beginning to change in ways that the ecosystem could not absorb. The Tethys Sea, the shallow tropical ocean that bordered the northern edge of the Kimkim floodplain, began to transgress southward. Marine waters advanced over the coastal lowlands. The river systems that had drained into the Tethys were disrupted. The floodplain environments that had sustained such extraordinary productivity began to fragment, to dry, to change character in ways that reduced the abundance of the aquatic prey that had been the foundation of the whole ecosystem. The giant sawfish, Onchopristis, disappears from the Kimkim record at roughly this time. So do the enormous coelacanths and the giant lungfish. The prey base that had sustained the river giants began to contract, and as it contracted, the predator community that depended on it could not be sustained. Carcharodontosaurus disappears. Sarcosuchus disappears. Deltadromeus disappears. And Spinosaurus aegyptiacus, the largest predatory dinosaur that has ever lived, disappears with them. Not all at exactly the same moment, and the precision of the dating is limited by the resolution of the geological record available, but within a relatively narrow geological window, the extraordinary predator community of the Kimkim was gone. An entire ecological world, one that had no equivalent before and has had no equivalent since, ended. This was not the end of Spinosaurids as a family. Other Spinosaurids, smaller and more broadly distributed, persisted in different parts of the world for tens of millions of years after the Kimkim community collapsed. Irritator challengeri lived in what is now Brazil. Ichthyovenidor laosensis lived in what is now Laos. Vallibonavinatrix cani lived in what is now Spain. The Spinosaurid lineage was not extinguished with Spinosaurus aegyptiacus. It continued, diversified in smaller forms, and eventually disappeared in the late Cretaceous for reasons that are not fully understood. But none of these later Spinosaurids approached the scale of Spinosaurus aegyptiacus. None developed the same extreme anatomy. None occupied the same ecological role. The specific combination of size, aquatic adaptation, and ecological circumstance that produced Spinosaurus aegyptiacus was a one-time event. It happened once, in one place, under one specific set of conditions that lasted for a geologically brief period and then ended. It will not happen again. The line of descent that connects Spinosaurus to the broader tree of life did not vanish entirely, of course. Spinosaurus was a theropod dinosaur, and theropod dinosaurs did not go extinct 66 million years ago. The avian lineage, the birds, survived the asteroid impact and radiated into the extraordinary diversity of species that fills the world today. In the technical sense, the lineage that produced Spinosaurus still has living representatives. Every bird that has ever caught a fish, every heron standing motionless at a water's edge, every pelican diving into a wave, carries within it the deep evolutionary heritage of the theropod body plan
that Spinosaurus took to its most extreme expression. This is not a poetic metaphor. It is a phylogenetic reality. Birds are theropod dinosaurs.
The evolutionary distance between a heron and Spinosaurus is enormous, and the anatomical differences are vast. But the connection is real, and it is direct. The long, narrow skull of the gharial-beaked heron, tilting toward the water surface in search of fish, echoes something of the skull of the giant that hunted in the rivers of Cretaceous North Africa 95 million years ago. The echo is faint, but it is there. What remains of Spinosaurus in the more literal sense, the physical fossil material, is frustratingly limited for an animal of such scientific importance. The original stromer material is gone, burned in 1944 and irreplaceable. The photographs and drawings and written descriptions that survived are invaluable, but they are shadows of the original evidence. The Moroccan material, the bones collected from the Kim Formation that formed the basis of the 2014 reconstruction, exists in museum collections in Italy and Morocco. Some of it has been the subject of ongoing preparation and analysis. New pieces of the puzzle continue to emerge from the formation as fieldwork continues, though the pace of discovery is constrained by the difficulty of working in the region and the ongoing problem of informal collection that removes material from its geological context before it can be properly documented. A partial skull, discovered in the Kim and described in a paper published in 2018, added important new information about the rostral anatomy of Spinosaurus, confirming and refining details of the skull shape that had been inferred from more fragmentary material. The skull showed the characteristic elongated, low-slung profile, the retracted nostrils, and the conical teeth that had become the defining features of the animal in its most recent reconstructions. New vertebral material, recovered from the Kim in the years following the 2014 paper, has allowed researchers to refine the reconstruction of the dorsal structure. The details of how the neural spines were shaped and spaced, and what that implies for the appearance of whatever structure they supported, continue to be debated and refined as new material is described. And the footprints. The trackways from the Kim Formation that were described in the 2020 study represent a category of evidence that has barely begun to be exploited. Ichnological surveys of the formation have been limited, and the potential for new trackway discoveries that could shed light on Spinosaurus locomotion, behavior, and habitat use remains enormous. In 2023, a new study using microcomputed tomography, the same imaging technology used in medical CT scanners but applied to fossil bone at much higher resolution, examined the internal structure of Spinosaurus teeth in unprecedented detail. The results revealed growth patterns and wear features that provided new information about feeding behavior and prey type. The internal structure of the teeth was consistent with repeated contact with hard, resistant material, the kind of wear you would expect from an animal that regularly encountered bone or the armored scales of large fish. The study supported a diet dominated by large aquatic prey, but did not rule out occasional consumption of harder-bodied terrestrial animals. Each new study, each new specimen, each new application of technology to existing material adds another layer to the picture. The picture is still incomplete. It will be incomplete for a long time, possibly forever. But it is richer and more detailed than it has ever been. And then there is the question that every paleontologist working on Spinosaurus carries with them as background noise. The question that has been asked at every conference and in every laboratory where this animal has been seriously studied. Is there a complete skeleton out there somewhere? The Kim beds extend across a vast area of southeastern Morocco, most of it unexplored at the level of systematic paleontological excavation. The informal fossil hunting that has produced so much of the known material has, by its nature,
been concentrated in areas that are accessible and that have previously produced good specimens. Enormous stretches of the formation have never been surveyed by professional teams with the equipment and methodology needed to find and properly document articulated skeletal material. Articulated Spinosaurus material, bones that are still connected as they were in life, preserved in the position they fell rather than scattered by water or scavengers, would be transformative for the field. An articulated skeleton would confirm or deny the proportions of the current reconstruction with a certainty that isolated bones cannot provide. It would show the relationship between the limbs, the spine, the skull, and the dorsal structure in a way that composite reconstructions from separate specimens inherently cannot. It would resolve, or at least dramatically constrain, the debates about locomotion, posture, and body plan that have occupied the field for a decade. Whether such a skeleton exists and whether it will ever be found, nobody can say. What can be said is that the search is ongoing. Nizar Ibrahim and his colleagues continue fieldwork in the Kemkem. New teams from Moroccan universities and international institutions are entering the field.
Remote sensing technology, including satellite-based geological mapping that can identify fossil-bearing rock formations from orbit, is being applied to North African formations to identify new targets for excavation. The methodology is improving. The coverage is expanding, and the Sahara gives up its secrets slowly and on its own terms. There is something fitting about the pace of discovery. Spinosaurus has resisted easy understanding for 100 years. It destroyed its own evidence by existing in a place and time where the fossils it left behind were fragile, scattered, and difficult to find. It confounded every attempt to place it neatly in an existing category. It violated the expectations of what a large predatory dinosaur was supposed to look like and how it was supposed to live. It drove the scientists who studied it to frustration and brilliance in equal measure. That is not going to change. Whatever new discoveries emerge from the Kemkem in the coming years, they will add to the picture. They will not complete it. The animal is too strange, the record too fragmentary, the questions too fundamental for any single discovery to provide final answers. But consider how far the understanding has come in 100 years. In 1915, Stromer had a partial skeleton of uncertain proportions, no analogy for the dorsal structure, and no ecological context. He named an animal and described its bones and admitted freely that he did not fully understand what he was looking at. Today, we have isotopic evidence of semi-aquatic lifestyle. We have bone density data calibrated against a database of hundreds of living and extinct species. We have a biomechanically tested tail model showing aquatic thrust generation. We have footprints showing the animal alive and moving in water. We have computational fluid dynamics models of swimming locomotion. We have CT scans of teeth showing dietary wear patterns. We have phylogenetic analyses placing Spinosaurus in a lineage of spinosaurids that showed aquatic adaptations across tens of millions of years of evolution. We have an ecological reconstruction of its environment that explains, at least partially, how an animal of this size and with these adaptations could have survived and thrived in the rivers of Cretaceous North Africa. We have, in other words, not a complete answer, but a genuinely extraordinary partial one. And the partial answer is more surprising, more complex, and more scientifically interesting than anything Stromer could have imagined when he spread those bones across his laboratory table. Spinosaurus was not the theropod that ate fish as an afterthought. It was not the sail-backed oddity that existed at the margins of the Cretaceous world. It was the apex of a long evolutionary experiment, a lineage of predators that had been moving toward the water for millions of years and that, in Spinosaurus aegyptiacus,
produced something genuinely unprecedented in the history of large terrestrial vertebrates. A giant that had turned its back, in an evolutionary sense, on the land that its ancestors had conquered. A predator that had found a new way to be the largest, most dangerous thing in its world. A creature that challenges every assumption we bring to the study of what a dinosaur was supposed to be. The rivers of Cretaceous North Africa are gone. The Tethys Sea that bordered them dried and shifted and became the Mediterranean and the Sahara and the Atlas Mountains. The world that produced Spinosaurus has been so thoroughly transformed by 95 million years of geological change that almost nothing of its physical structure remains recognizable. But in the stone, in the sandstone beds of the Kimkim, in the fragments that emerge year by year from the desert that was once a floodplain, the evidence persists. Slowly, incompletely, maddeningly. And in laboratories in Milan and Chicago and London and Casablanca, scientists are still arguing about what it means. 100 years of argument, a century of contradictory evidence, revised reconstructions, destroyed fossils, informal excavations, international controversies, and spectacular discoveries. 100 years of an animal that refuses to be understood on anyone's terms but its own. That is the story of Spinosaurus, and it is not over yet. What do you think? Is Spinosaurus primarily a fish-eater, an ambush predator of large dinosaurs, or something more ecologically flexible than either of those categories captures? Was its dorsal structure a sail, a hump, or something we have no modern analogy for? And what do you think a complete, fully mature Spinosaurus skeleton would show us that would change the picture most dramatically? Leave your thoughts in the comments. The debate is 100 years old. It could use a few more voices, an analogy for. And what do you think a complete, fully mature Spinosaurus skeleton would show us that would change the picture most dramatically? Leave your thoughts in the comments. The debate is 100 years old. It could use a few more voices.